Okay. So welcome everybody to this new series of the ONEPAS seminar, and especially the new people who are joining here for the first time. So we're going to have this session, and for the next 5 weeks, being managed by Rafael de la Llave, and he's going to talk about constructive methods for the long-term analysis of dynamics. This is the overall arc of this series of lectures. Just to give a few pointers, if you want to ask questions, type them on the chat, and we'll get to you. And everybody's going to be muted, but if there are questions along the way, we'll make sure to get them to the speaker. Okay, so without further ado, let's hear Rafa, and it's all yours.
Okay, well, thank you very much for the opportunity to speak here. It's very nice to be able to talk to an audience. And of course, one of the things here that in this new world, etc., is that I don't see the reactions of the audience. So please make the largest effort to be as vocal as possible and to let know if anything happens, right? So this is very informal and I kind of prepare it. And I already realized that the first mistake, of course, the French people know that vignettes should have two T's. So I wanted to emphasize that I mean, I am not going to try to give a survey, right? And I mean, of course, this is 5 lectures, etc. And I will tell you it's a very big subject. So I'm just going to tell 2 or 3 examples that I like, that I happen to like, and you know, that's it. So no, I mean, and if you tell me why didn't you talk about all this and about the other, well, you know, what can I say? So this is just a few examples, no survey and whatever. So things that I believe that can give you the flavor. And well, so dynamical systems started because people tried to predict the future, but this is not an easy problem. And in some cases, like for example, in astronomy, things are reasonably easy to predict. I mean, it took many hundreds of thousands of years of evolution, but I mean, 5,000 years ago or so, people knew how to look at the stars and realize the periods of the stars and the sun, etc., right? And things were pretty organized, etc. But on the other hand, this is something that was even discovered and it started hitting people in the 60s or the 70s, that in many cases of interest, this predictability can disappear very rapidly. And the things that are surprising, I mean, people knew that this could happen, but the thing that really started being striking is that this loss of information happens very rapidly, exponentially fast with a back exponent, and that this is very abundant. And then we want to sort of try to sort of develop new tools, right, to cope with that, and in particular statistical mechanics and computations, etc., and new ways of thinking. And that's, you know, I want to sort of discuss a few of the new ideas. And the geometric program for dynamical systems is much older. I mean, you can certainly try to do it you can trace it back to Poincaré. So the first idea is to try, I mean, if you cannot predict everything, right, then try to sort of predict something. So you find a few things that start to behave reasonably easily, and then you sort of try to build up on that, right? So, I mean, you know, we all have heard about chaos, and I could get some pictures, etc. But you try to sort of find just a few things that you can understand. And the things that you want to understand are things that you can establish with a finite calculation, and then they imply something for all times, right? So this is the type of things that you want to understand. Things that actually have a very big payoff, that you perform a finite calculation and then you can, and I already found another mistake, so imply very rich. It's V-R-I-C-H. Okay, and then I will be trying to describe several techniques, right? And there are other people that are going to give other lectures, and I will discuss some of them. And we have three basic type of techniques. One is analysis, topology, and computational methods. And then, as you will see, then we have been covering other things over here. And there is a sentence that I heard from somebody, and I cannot remember who it was, is that dynamical systems is a problem and is not a subject. So in many ways, people that are, you know, some type of mathematicians that like category theory, etc., they get horrified because, I mean, you know, if you're interested in dynamical systems, you're interested in predicting the future. And then one day you write a paper using algebra, the other day you use a paper using measure theory, etc., etc. Okay, so that's why it's very rich, etc. And I cannot give flavor of the richness of the subject, so I just decided to pick a few things and then try to tell you some examples. I mean, actually, I think it's very pretty because I think I am going to give 3 proofs in this lecture. But let's see how it goes. All right. And then, as I was telling you, I'm not going to be terribly systematic about everything. So I'm not going to give you the sharpest results and things that are true in situ. Maybe I will do them only for analytic things or things like that. And of course, I cannot be a survey. And then, as I will tell you some of the things I just took from other papers. All right, so this is more or less what I am going to try to, so in the talk today, what I am going to try to do is explain you what are 2 things which are stable manifolds and topological horseshoes. And then I will try to do in the second lecture, which I will do is hard implicit function theorems. And then in the third lecture, Alex Arrow will try to explain things that you can use. And I made a mistake, sorry, another mistake. So in point number 4, the lecturer is Marian Guidea. Sorry, I apologize to Marian. But it's correct in the things that count. And then in the last lecture, Yachi Yang will start explaining something which I think it's also of great interest in Brown, about state-dependent delay equations and equations for electrodynamics. Electrodynamics, it's a very big problem because it has delays, and the delays depend not only on the position, but also on the trajectory. So then this is the type of things that Yachi will explain. Okay, there are other sources, and I wanted to mention several things that are very close to, I want to make propaganda, so that you get an idea of how rich is the subject. So there is a seminar organized in Montreal and in other places. So this is the research seminar and it's still going, so that people want to look into this. There is also a very rich source, which is the computer assisted proofs in dynamics, which is a very rich library, and you can use it to do numerics, etc. And then if you want to look at other things, I recommend, well, you know, these are kind of disjoint, but in like 10 years ago, this is disjoint, but it's kind of the same style. I gave a few lectures in Minneapolis with Peter Bates and with Alex Arrow and several other people. So we had a lot of lectures more or less in the same style, but I made a point of making them completely disjoint. And then if you want to look into something which is a very constructive proof of KAM, which I have given to undergraduates, you can get them in these places. So there are 2 I mean, this is something which I think it's an accomplishment by now. I mean, not only due to me, of course, but you can give a complete proof accessible to undergraduates of the KAM theorem, which is in about 3 hours for undergraduates. So you only assume things like the undergraduate analysis or undergraduate complex analysis, and then you can get them. You can give a complete proof. All right, so there are many objects, etc. So, you know, you can talk about fixed points, periodic orbits, etc. I was making a list of several things that you can study, etc. I will just concentrate on a couple of them, and I will try to sort of try to describe the things. So there are two types of flavors, and this is a disclaimer a little bit on the technical side. So people argue quite a lot about whether you use continuous time or discrete time dynamical systems. So the continuous time is what appears very often in practice in when you have a differential equation, and if you have a differential equation, then it involves, so it defines an evolution in the sense that if you have an initial condition, and if you consider the final solution as a function of the initial condition, this turns out to be a diffeomorphism, and the diffeomorphism satisfies the semi-group property, and this is what you study. So this is what people think about as dynamical systems, but a version that is actually quite useful, and actually for lectures is much better because it allows you to make pictures in a much easier way, is that you consider the discrete time. You look at the time and you look at the things only every second. This is what people used to call the stroboscopic map, right? So that like the people that used to go to discos in the 70s or 80s, then you know what's an stroboscope, right? So then you see the things when there is a very big flash, etc., and then you see the thing happening, etc. And roughly speaking, the two things are equivalent, but for the point of view of presentations, they are mathematically equivalent, but it's a little bit easier to do pictures and do things in these things over here. And so let me try to tell you a little bit of, this is something that everybody knows, but there is the Brouwer fixed point theorem, which is if you have a continuous mapping and if it maps a ball to itself, then it has a fixed point, right? And the interesting thing is that, of course, if you have a fixed point, then you know the behavior of this point very well, right? Forever. So once you know that there is a fixed point, then you know that there is one point in which you can predict what will be happening in 1,000,000 years or 1,000,000 iterations, right? Okay, so this is one example of something that you can verify, which is very nice to verify, very easy to verify, to check that a ball gets mapped into itself. Then you can allow yourself errors. I mean, if the ball is size of error, if the size is, if you have a ball of size 1 and then it gets mapped into a ball of size 1/2, then you know you can do your numerical calculations, and provided that your error is not bigger than what you match go in, then you can verify this calculation. So the verification of the hypothesis can be done with a finite precision calculation, and if you change f, the hypothesis remains. So everybody knows a version of this, and we teach it even in undergraduates, etc. And this is one topological argument, and you know that modern proofs require you do with index, and there are many versions of index, there are whole books, etc. And they obtain different type of conclusions. So for example, if you use Leray-Sauder, then it has a very good dependence on parameters. All right, so let me try to tell you a little bit more about so this is this is a theorem which is very important, which is that suppose that you have a fixed point, etc., right? I mean, this is the idea. So you know everything about a fixed point. This is not extremely useful because you say, well, a point is a very small thing, right? Because a point, just knowing a lot about one point is basically, you know, being extremely specialized is not extremely useful. So let me try to, so this is kind of one of the first theorems that are important. And I don't know if people see my pointer. People see the pointer? Yeah, thank you.
Yes.
So just start, and the hypothesis, I am not going to be very careful about the hypothesis. Let me put analytic here. There are versions. Okay, so you have a fixed point, and I am putting the fixed point at 0. And then I just introduce a notation because I don't want to be writing df of 0 all the time. So df of 0 is the linearization, right? And I write it as A. And then the map, it has the linearization and a nonlinear part, right? And the nonlinear part is 0 and the derivative is 0. And of course, the intuition is that when x is small, the nonlinear part is sort of negligible. Right? When x is small, this is much, the n is much smaller than this part, and this is the thing over here. So I am assuming that the spectrum doesn't contain any eigenvalues of modulus 1. For the differential equations people, the corresponding assumption for differential equations is no purely imaginary eigenvalues. And then you can decompose the space into the stable and unstable components, which are the spectral spaces corresponding to the stable and the unstable solutions, right? And then the conclusion, which is very surprising, is that it's equivalent to say that the orbit remains bounded, and then to say that belongs to an stable manifold, which is an analytic manifold. And there is something that this didn't show up, and so I'm sorry. It's a manifold which is tangent to ES, right? So this is kind of a little bit a surprising thing in the sense it's amazing, because you have some very crude hypothesis, which is boundedness, and then tells you that you have to be on a manifold. And actually, I mean, this is not so surprising in the sense that this is what happens if you have a linear mapping. So if you have a linear mapping and then you iterate it, then if you remain in a neighborhood, then you know because you belong to the stable manifold over here. And then if you take into the following, and this is something which is extremely surprising in my opinion, and this is one of the things that annoys the people that believe in category theory, is that if you take the backwards iterates of these things over here, then it's an inverse manifold. I mean, it doesn't cross itself, right? It's an inverse manifold. And then there is something really amazing, which is that a point belongs to this stable manifold if and only if it converges to 0. The reason that this is amazing, and you will see that you get a lot of things, because this hypothesis is topological, but this one over here tells you that you belong to an analytic manifold. So you belong to an analytic manifold by topological assumptions. This is amazing. I mean, you know, it's a proof, etc. So, I mean, eventually it will become trivial, but if you look at it and you have never seen it, then I think it is an amazing thing. And actually, it's an amazing amount of bootstrap. It's an amazing amount of bootstrap. You start from a topological characterization, and then you get that the thing is analytic. I mean, for the people that are analysts at heart and they like bootstrap of regularity and things like that, this is an amazing amount of bootstrapping. And it also has geometric continuity. So what I am going to try to do is to give you a proof. I mean, there has been lots of progress in this sort of things, and I want to give you a very constructive proof, and it takes 3 slides. So let me try to go over it, etc. And so, as I told you, I am going to do the case when n is equal to 2. As I told you, I am going to do only vignettes. So, you know, I stated the theorem in Rn, but I am going to cheat and only give you the proof in R2. And I mean, it's not a big cheat, but it's just the basic idea. So you denote, so this has an eigenvalue, and let's say that it's an stable eigenvalue. And I point to you that the eigenvalue is unique, but the eigenvector is a multiple. So the eigenvector is not unique. And now the thing that I am going to do is I am trying to find a K which is analytic in the unit ball in such a way that it satisfies this functional equation. And I will tell a little bit about the history of this functional equation. It's very interesting, the history. And the equation tells you that F composed with K is equal to K of lambda T. Okay, so some of you have seen these things. If you put over here, K has sine and cosine, k is sine and cosine. So this is the formula for duplication of the angle. So if you know k of t, then you know k of 2t, right? There are these easy formulas of duplication of the angle, but this is an equation that I want to study. So f composed with k is equal to k of lambda. Okay, now the thing that I want to mention, there is one of the things which is interesting to remark is that this equation is underdetermined, because if you scale k, then it still is a solution, right? So okay, so it's an undetermined equation, and then some people are bothered because you don't get uniqueness. But I mean, if you're trying to solve a problem, uniqueness is not a good thing. So if you have several solutions, then it is better. You know, uniqueness is sometimes overrated. So let me try to write the function like this. So let me try to, this is something that every analyst knows how to do. So you write the dominant part and then the part which you consider it's kind of small, right? So when you write the dominant part is the linear, and then you put the higher order thing. So I am putting k1 of t, and k bigger is the things that have power series that are exponent bigger than 2. And then when you plug all this into the invariance equation, I will call this the invariance equation, right? I mean, so let me also, sorry, I should say that if you have a point k of t, so this is a point in the range of the manifold, then you hit it with f, and then you get another point in the manifold. So the range is invariant, right? Okay, for the people in ergodic theory, then people say that lambda is a factor of the dynamics or something like that, right? Or semi-conjugate, right? There are all these sentences, but geometrically what it means is that if you have a point of the form k of t, you hit it with f, and then you get another point of the same form. And if you plug this idea, which is very nice it's very natural to analysts to separate the small part from the big part, then you obtain that this equation amounts to two things. One is that ak minus ak bigger is equal to n of alpha plus these things over here. And alpha, as I told you, it's underdetermined because the eigenvalue equation is underdetermined, right? The eigenvalue equation is underdetermined, and then if this is underdetermined even for the linear case, then it's going to be underdetermined for everything like that. So then there are these two equations, and if you're an analyst, then you realize that this part is kind of negligible, etc. So then it's very nice to sort of try to invert all this and then put it back into the things over here. So here we need to sort of do a little bit of analysis, right? So, and of course, there is another mistake. This should be a parenthesis. Okay, so you look at this operator, which is the left-hand side of the main part, etc. And I am going to claim that it's boundedly invertible in a norm, which is just, let me take the L1 norm in analytic functions. So this is an L1 norm. It's very well known. And the interesting thing is that this L1 norm is satisfies Banach algebra properties. So you know these things over here. And now what I claim is that this operator, it's invertible. And the fact that it's invertible is very simple, because you equate like powers of t, and then you obtain auj, which is the coefficient, is equal to, so you try to solve an equation u equal to eta, lu equal to eta, and then you try to find it. So if you take this equation and then you expand it in powers, if you expand it in powers of t and equate like powers, the power corresponding to lambda t is lambda j u to the j, and this one is just auj. And then you obtain these things over here, right? So there is another mistake. This should be a -1, right? And if this lambda j is an unstable eigenvalue, the other ones are unstable, so you can always solve it. And so this is this thing is bounded. Yeah. Sorry, I mean the complication here is that I made a couple typos. There is a -1 missing here, and this h should be a parenthesis. Okay. But and now the equation that we wanted to do becomes very easy, because you just invert the thing that you knew it was invertible, and this is a very natural thing to do, because you know, this is what you do if you're an analyst. You look at the main part and then you try to invert the main part and then make everything into a fixed point. Okay, and then using that n is quadratic, so this is bounded and this is quadratic, so you look into a ball of sufficiently small radius, then it gets mapped to itself, and then it is a contraction. So that's the story. So the conditions are not terrible, and so this is a proof of the stable manifold theorem. I mean, it's a complete proof in the case when n is equal to 2, right? But I think it's kind of the right idea. So there is several things that I want to maybe point out. One is that this proof is based on the contraction mapping principle. And then if you get something which is based on the contraction mapping principle, I mean, just the simple one, the Banach one, not fancy things. So this is a contraction, etc. And if you have numerically a very approximate solution, you have something that you plug it into the equation and it satisfies it up to a very small error, then you know that the true solution is very close to these approximate solutions, and then the algorithms can be validated. So this actually gives you the remark, etc. Let me make a couple remarks. Well, one remark which is interesting is that if f is a polynomial, then k is entire. And the reason is because if f is a polynomial, then you can always apply f. So that means that you can always find the function defined in a certain domain. And then the argument also gives a proof actually of a generalization of the stable manifold theorem. So provided that lambda j is not an eigenvalue of A, then you can get it. And actually you can get even more. And if f is differentiable, then you can obtain CRK very easily, because the only thing that you need is that this operator n is a contraction, etc., and it's a contraction, etc. And then in higher dimensions, then you're required to use multi-index notations and things like that, but it also works. In infinite dimensions, it's also possible, but then you need a fancy spectral theory, and then one of the surprises in going into this proof into infinite dimensional theorem, then it is that this requires to take care of the residual spectrum. So there are some references. So one version of it is the story of this equation is very interesting, because this was studied by Poincaré, and actually Poincaré used it because he wanted to get to solve the quintic equation and the quartic equation explicitly. Of course, you know that you cannot solve the quintic equation using radicals, but if you define new functions and the functions satisfy this equation over here, an equation like this, then you could solve the quintic using fancy functions that satisfy these things over here. So roughly speaking, this functional equation f composed with k equal k composed with lambda of t is more or less like the duplication of the angle formula. And Poincaré rediscovered, I mean, of course, Poincaré was he's my hero, but he didn't know about Banach. He didn't know about the Banach contraction mapping principle. So the proofs are using the Majoran method, and they're really ugly, and especially in higher dimensions. But anyhow, so and in the book, and there is a very funny story, because he rediscovered that and started using it a lot in the book in differential his books in celestial mechanics. But amazingly, he quoted the wrong paper. So he referred people to the wrong paper rather than referring to this paper in which he studied this functional equation. And then I think that it was very hard to sort of trace it all back, but now I think so if you want to read the story, in this paper, we kind of retrace the story, and then we rediscover what was going on, and how come that Poincaré was referring to the wrong papers and nobody figured it all out. And there is a very big survey by Alex Haro, Marta Canadell, Jordi Luis Figueras, Alejandro Luque, and Josep Maria Mondelo, which it's a whole book about how to use similar tricks for many things. All right, any questions? I mean, I have been talking too much. I think nobody has said anything, and I cannot see faces, so I am completely. This is very disturbing. So I am going too fast, too slow. Fine.
It's good.
So, you know, you saw a proof of the center manifold, or you saw a proof of the stable manifold theorem in like 10 minutes. So that's, I think, maybe this is like a Guinness record. So the next thing that I want to discuss is what it's everybody's favorite version of the something that you get lots of things for anything, right? And so this also has a story that starts with Poincaré. So in the three-body paper of Poincaré, he discovered it, and then there is all these stories about scandals with prices, etc., etc. So this tells you what happens with prices, right? Yeah, I was looking at the price of this King Oscar prize, right? And if you look into the King Oscar prize, it tells this is for a working on the either on the three-body problem or in automorphic functions. So you can guess that the priest that they knew who to give the prize, right, before, because it was asked for a memoir either in three-body problems or in automorphic functions. So so this was discovered, and actually he used it quite a lot, etc. But it was not very clear because there is something that you have to look. So this is called consequence. That's what Poincaré used to call all this theory de consequence. But it's basically more or less what I am going to present. And then Cartwright and Littlewood, they found it in a paper, which is a very interesting paper because it's, well, especially when you look at the paper number 2 that was published in the Annals, it's so badly written that they ended up having to publish a set of erratas. So I don't feel that bad about having found all these mistakes in these slides, if you compare with the paper of Cartwright and Littlewood, etc. So, and then the big revolution is when Smale discovered a geometric interpretation of it. So let me try to go over this story. So I'm going to present actually two proofs. So I'm going to present an analytic proof and a topological proof, which I took from these papers, right? And I point out that there is a much more sophisticated theory, which I am not going to cover. As I told you, I am just going to get two interesting things, two interesting proofs. And the thing that makes it beautiful to me is that you can get quite a number of orbits, actually an uncountable set of orbits, and that you can go at it either using analytic methods or you can use topological methods. And the two of them can sort of work together. And in modern times, there is a much more sophisticated theory, which I am not going to cover. But you know, if people want, I will be very happy to explain what I know about it. I mean, you know. Okay, so this is basically what it's a homoclinic point, right? Transverse homoclinic point, I should say. So this is a point in which you have computed the stable manifold, right? I was putting it in a plane, and there are, so let me not claim anything beyond the plane because that's the place where I can make drawings. So you have computed segments of the stable manifold and segments of the unstable manifold, which you do by applying the same result to f to the -1. And they happen to intersect. Okay, there is not, I mean, I told you that the stable manifold doesn't cross the stable manifold, right? So you cannot get these things crossing to each other, but they happen to cross. And this is something that you can establish with a finite calculation. So you get your computer, or if you are a very good person, you can sit down and do it. And I remember when I was in the early 80s, I mean, Misurevich and several other people, they sat down and by pencil and paper, they managed to prove that the Henon map has a homoclinic point. And we were all very amazed, etc., you know, because, but nowadays it's very easy how, I mean, it was a very big accomplishment, of course, at the time. but it's something that you can do with a finite calculation. And in the Genon map, Misurevich did it with pencil and paper, and there is no question that that's a proof, because it involves, composing a quadratic polynomial with a quadratic polynomial, things that we don't typically like to do, but it's okay. So this is something that you can establish with a finite calculation if you compute these things. And I remind you that thanks to Banach contraction mapping principle, if you do these things that I was telling you, then you can get a finite error. And then the interesting thing is that these things that you obtain with a finite calculation, has an enormous amount of consequences, right? So in particular, I can produce an uncountable number of periodic orbits. So this is an amazing type of thing, which is that with a finite calculation, then you can produce an uncountable many periodic orbits, and these uncountably many periodic orbits, you can be even very quantitative about it. Okay, so the first remark is the following, because the manifolds are invariant, right? So you see, you start with this point and then you iterate, so you have to have a picture that more or less looks like this, right? Because, I mean, this point is in the stable manifold. You take an iterate, and on the one hand, it has to be moving, right, inside, because it's in the stable manifold. But on the other hand, it has to stay in the stable manifold. And the only way that this can happen is that if this goes like this, right? So the unstable manifold has to bend, and then this thing has to go to the iterate, right? So this is the point P, and this is f of P, and then f square of P, for the same reason, stays in the manifold, and then things keep on going like that, right? Okay, so something like this has to happen, that these manifolds have to iterate, and this is just a consequence of the fact that these manifolds are invariant, and that the motion along the stable manifold is roughly moving towards the thing. So the thing that I am going to do just for fun is let me draw a small thin rectangle here, right? So let me draw a small thick rectangle that I put here in green, right, around the stable manifold, and it more or less goes like this, as I was telling you, etc. And let's make it really thin, and I am not going to be extremely careful about it, etc. But very quantitative, but you can see that the things that I am telling you happen. So the thing that happens is that these points over here, all the points over here are going to be marching towards the origin, but then this thing over here that was very thin is going to expand, right? Okay, so this is the thing that happens if you put all this business of a little bit of a little box, and then eventually this is more or less what you are going to happen, right? I mean, this is a schematic, right? But the direction here is going to be contracting, and then this thing over here is going to be expanding. I mean, I have some pictures that I was doing in realistic systems like the Genon, but you cannot see anything really, because things are a little bit ugly and the things are not informal. But qualitatively, this is what happens. This direction contracts, this other direction expands, and then the thing that used to be a thin vertical box becomes a long horizontal box, right? And then you keep on doing things, and then eventually these things keep on, and then these things start to become thinner, but then they start propagating along the stable manifold, and then you get something like this. And just for the fun of it, so let me tell you, this is, of course, I rearrange it, etc. And then I prepare it over here. So this is the famous horseshoe, right? So if you put some lines over here, let me just put some vertical lines over there, some edges into this rectangle that I was putting, right? And I put them here in magenta. So this thing over here, right? This thing over here, it becomes this edge becomes this edge, and this other edge becomes this other edge, right? So the rectangle is kind of getting squeezed and changing orientation, right? And then the edges go like I was saying before. So let me make a cleaner picture. Okay, a clean picture of the behavior of the iterate is I have a rectangle. I mean, if you're a topologist, this doesn't bother you too much, right? Because that's the picture of the horseshoe, all right? So the picture that you have is that you have a line over here. So you have a rectangle, and then I have marked two edges that I am going to call L1 and L2. And then when you expand them, etc., so there is an iterate of the original map that sends it into this horseshoe. And the interesting thing about the horseshoe is that the two sides go like here and like there, right? And that there are these two regions that I am calling left and right, okay, which are contained between the edges of the rectangle and the two sides that I had marked, right? And the interesting thing is that if you want to go from here to there, right, if you want to go from here to there and stay into the image of the rectangle, then you have to cross from L2 to L1 and from L1 to L2. So that's a topological picture, right? And this is the crucial thing, right? Okay. And one remark that I mentioned is that I proved for you, more or less, right, that I proved for you, well, after waving my hands, etc., but it can be a very easy formal proof, that if you have a homoclinic point, then you find this thing. Now, you could find these things for other reasons, right? And actually, there is also something that satisfies the assumption, and it's much so this is one of the things that it will be very hard to deal with analysis. This is the situation, right? And now the theorem that I want to, let me just try to say. So this is the theorem that if you have a rectangle, and of course it's a topological rectangle with two marked sides, and then you have this property that I told you, right? So the amazing thing is that if you sort of, and this is the conclusion. So you fix any path, right? And then you fix any sequence between right and left, okay? And then there is an orbit that follows this dance in the path. So this is sort of amazing in many ways, and this is the thing that goes into determinism, because you could have an orbit that stays like 50 million times on the right and then switches to the left 100 times, right? And then goes to 72 million times into the right, and then goes into 100 millions to the left, etc. So you can prescribe any sequence of right and left, okay? You can prescribe any sequence on right and left, and then there is one point that satisfies all these dance. And moreover, the set of points that satisfy all this dance is actually quite big, in the sense that you cannot avoid them by making into a path. If it was an isolated point, then you could choose the path gamma that joins these two things and avoid it. But this is something that basically obstructs, that that it cuts across and you cannot go around, right? Okay, and it cuts across in a very strong way because you cannot avoid it even with continuous things in the future. Okay, and the proof is amazingly simple. The proof is amazingly simple. I mean, it comes from this book of, from this paper of Kennedy and York. So you find the gamma, so you fix the gamma, and then because all the things, then you can find a segment that crosses. So let's pretend that I am trying to hit the first element in the sequence is right. So I can find a segment that does it, right? Because that's the story. Now you look at the image of it. Okay, now you look at the image of, so now you look at the image of f of gamma 0. So this is a very close interval. So that's a close interval that joins one of the edges to the other edge. And so the image has to go and do something like this, right? And therefore, you see, then this path has to go, this path f of gamma has to include the right and it has to include the left, right? So you can select a subpath that selects the left. So I am trying to do the sequence which is right and left, right? And this path over here corresponds to a previous path over there. So the ones that satisfy, so if f of gamma 0 satisfies this, then you just take a close interval there, right? Yes? So this interval here and the ref goes into there, right? And you see that all the points that are in this path over here, they satisfy the fact that in the first iterator on the right and in the second iterator on the left. Yes? So you take another iterate of this thing over here. So this thing over here goes to the right, to the left. You take another iterate, which is the same as taking two iterates on this one, and then you go from the right to the left again. Okay, so you get a sequence of nested intervals that that basically do the dance, right? So you start thinning out these things, and by recursion, you see, because you have taken something that goes from one edge to another edge, once you take another iterate, then it goes around. And then by induction, then you obtain everything, etc. And then you have to use a topological theorem that says that whenever you have a sequence of closed intervals, then there is a point that satisfies everything. Okay, so I mean, I have gone it a little bit fast, but this is a proof, and I point out that this is an uncountable set of orbits, and some of them are totally unexpected in the sense that you can go to the right, to the left, and this, I mean, you know, if you have been going 30 million times on the right, then you can imagine that that you're going to stay forever, but no, you can just switch around. Well, I also want to point out that there is that these finitely many checkable conditions, then we obtain countably many orbits, and some of them rather bizarre, like staying for 50 million times on one side and then switching. And then I also want to mention that this configuration that a rectangle goes into another rectangle just across can happen for other reasons, not just for the homoclinic points. And then there is a software called Chomp, which is also a very useful software that you can download, and it's very good. Then you can actually try to find systematically for occurrences of these things. It's a combinatorial problem. And well, let me just not mention all this, but there is a complicated story which is different, which is using hyperbolicity. And then you have I mean, I have told you about the things that prescribe the dance in the future. So you can prescribe the dances in the past, and then it turns out that there is one thing that satisfies these things in the dance and in the past. And if you put extra assumptions, which I am not going to describe, which are hyperbolicity, this point is unique. All right, so I don't know. I think I am going a little bit. How much more time do I have? I have about 6 more slides, 7.
That's good. 5 to 10 more minutes. Yeah. All
right, so I'll try to sort of finish more or less in time. But I want to give you a second proof of a theorem like this, and this is based on, so this paper was based on Kennedy and York, these things that I told you, and you can read the proof. I put the paper there. And there is a theorem which is analytic, and this is something that has to do with the following story. So if you iterate many times, right? So you iterate, then you end up close to the point over here. And if you iterate backwards, then you end up also very close to the point, right? And then the basic idea that you want to do is to close everything. And if you close everything, then you obtain a periodic orbit of period n and m, right? So there is a little bit of an error. So this is an orbit, except when I decide to join from here to, when I decide to identify these 2 points, right? Yes, but if n is large and m is large, the 2 of them are close because both of them are close to the origin, right? Okay, so I have produced something which is very similar to a periodic orbit, right? Except that I have to cheat at one place, right? Yes? Okay, and this theorem tells you that you can actually justify everything that I was telling you, that you can justify everything, and that there is indeed a periodic orbit that satisfies that. So there is an orbit over here that sort of closes everything and so on. The interesting thing is that N and M are arbitrary. So you can get something that goes over here, goes here for a million times, and then it starts to go and goes back in 10, right? And then it stays there like another million times and goes back in 10 again, right? And you get another one in which you stay there 30 trillion and then go back in 10. Yeah. So that's why it's interesting. And the proof is also very instructive. And this proof is analysis, so that I want to sort of emphasize that you can go to these problems using either analysis or topology and sometimes both, etc. And the basic idea, and actually this is something that I will try to use a little bit more, which is that you think about, and I should have put over there not R but R square, sorry, I should have put an R square there with the subnorm. And then, so let me introduce this operator. And the idea is that a fixed point of this operator, so a point of this is a point is a fixed point of this operator if and only if it's an orbit. So that's a very important idea. So S is sometimes called the shift. And a fixed point of the shift is the same as being an orbit. I mean, this is, for, if you are doing differential equations, this is more or less the discrete version of the Picard method. But it's a little bit unfamiliar, but it's basically the Picard method. And then you use arithmetic, etc. So let me tell a little bit about this operator, which is very similar. So the observation is that if you take this orbit that I was telling you, you define these orbits with this approximate orbit. So this approximate orbit, sorry, it's a very approximate fixed point. This orbit that I was telling you, iterate 10 times and going back 10 times and etc. It's a fixed point because you are making an error only in the place that you are closing, you are jumping. This operator is very nice because if you look at the derivatives of the operator, and I should have put over here a second derivative, sorry. I mean, the derivative of the operator, I should have said that the derivative of the operator is very easy. I'm a little bit lost about it. I mean, but the derivative of the operator is very easy because I am getting a little bit lost. The derivative of the operator is very easy because when you change S, the only thing that happens is the derivative, and this should be a second derivative. Okay, and then the only thing that I need to do is to apply the fixed point theorem of Banach, right? Very easily. So if you have control, you have control on the second derivative, this should be the second derivative, and the only thing that you need to do is to check that this thing is invertible and that this thing is invertible irrespective of n and m with a constant which is uniform in n and m. And the derivative of S is very easy because that's what it is, right? And then to show that this minus the identity is invertible, then it amounts to solving this system of equations. And if I can solve these equations without any problem on the length, with estimates which are uniform on the length, then I win. And the answer is very, so I cannot do it in general, but let me try to do it in a particular case. So let me do it in the case in which the derivative is just A. So these derivatives at points are complicated, right? But most of the time are going to be just very close to the constant. So this is a toy problem. This is not the real thing. But once I solve the toy problem, then I can wave my hands and tell you how to do the general case. So the equation that you have to study is an equation like this. This equation is equivalent to two equations obtained taking projections over the stable and the unstable space, right? So this is the two equations that you obtain. And I put over here these things that I mark in red, then you can rewrite them and make them explicit. Yes. So in this one over here, then you get these things over there and the other ones, etc. And then you can solve them, just you can rearrange. This is just algebra, moving things from one side to another side, and these are the solutions by iterating, etc. So I mean, this is very simple idea. So basically, you are a Banach fanatic, and then everything that you do, you sort of turn it into a contraction, right? So you look at this thing. So this has two etas, right? So if you sort of make this eta explicit as a function of the other ones, this is a contraction. And if you make this eta explicit as a function of the other two, then it's a contraction, right? And then it's a contraction, and then you can write formulas like this. Okay, and then this proves the result. Okay, so I have cheated because the derivatives that I need to try to put, right, there is these things over here, but turns out, and I am not going to sort of explain it too much, but you can control the result, you can control the difference between the two. So you have a, I mean, this is very typical of analysis that you cannot solve the problem, but you solve a very simplified problem and then you control the error, right? Okay, and then we are going to try to do these things over here, and I think I am going to kind of I want to kind of finish more or less on time. So this is the argument to how to fix it, and I didn't do the details, but I mean, since the topologies managed to get an uncountable set of orbits, I just want to claim that the analyst can also get an uncountable set of orbits, right? Because you can take sequences going around in any way you like, but provided that you jump for fast enough time so that these small mishaps become small. So if you take a sequence, so you go around n times, then you escape m, and then you go around n2 and escape in m2, and so on and so forth, and you can keep on repeating all these things. But you can get orbits that you can get a true orbit that satisfies that. So, and this is again, and this is an uncountable set of orbits. And I was putting a periodic, etc. This is a little bit of the argument that was appearing also in Cartwright and Littlewood, but they were using topological methods rather than the fixed point method. Okay, so this is more or less what I want to discuss. So I have been using contraction mappings in the spaces of functions and in sequences and point sets, etc. And then this is the next of the set of lectures. So tomorrow I will be discussing, next week I will be discussing something that it's also some tool from the 60s, which is the hard implicit function theorem. So there are versions of contraction mapping principle. So they are not like the contraction mapping principle, because things are like contraction, but from one space to another and so on. They involve derivatives, etc. They involve losses of derivatives and things like that, and I will try to modify that, etc. And these hard implicit function theorems were started in the 60s, or mainly, Nash and Moser, and implicitly Kolmogorov and other people, and Jacques Schwartz. And then Alex Arrow will explain how can one use all this with computers. And Marian will discuss things that are topological arguments. So I try to keep a balance between topology and hard analysis. And then the last thing will be Yachi Yang, who will discuss how to deal with delay equations in some situations where you cannot get anything reasonable. But, my point is that if you think of this in some ways, I have given you maybe 2.5 proofs. The first 2 proofs were rather complete. In the second one, I cheated a little bit, but these things are not extremely. So that's why I said, they are not the most technically sophisticated results, but they are, I think, pretty illustrative of the ideas. Okay. And all right. So thank you very much. And I don't know if people are totally.
Okay, sorry, Rafael, in giving people the right to unmute themselves, I muted you inadvertently. Will you unmute yourself?
Mute myself. Okay, so I don't know if I managed to confuse everybody or breaking the record of giving the many proofs in a short time.
I think it was quite good. Are there any questions for Rafa? Comments? No. Okay, maybe I'll ask one. So in the last theorem you presented, when you want to compute like a periodic orbit or an almost periodic orbit for like big N and big M, if you want to try to do that like computationally, even an approximate periodic one, can you get things where the cost is very, I mean, if possible, independent of N, but if not...
Oh,
like...
it's very easy. It's very easy. No, actually, this is very practical, and I have used it actually quite a lot. It's very easy because you take the homoclinic point, and once you get the homoclinic point, I told you how to construct the approximate periodic orbits. Because you take the homoclinic point and then you iterate, and then after you are tired, then you jump into so you iterate in the periodic point. So you take the homoclinic point, then you iterate forwards and backwards, okay, and then you mix and match, and this gives you the approximate periodic orbit that you want.
I see.
Very easy. So you take this, whatever, you know, you have a million things forward and a million things backwards, and then you say, what is my favorite number? 75. I mean, you have to check that the numbers are big enough. So if, but once you check that the numbers are big enough, then you have your approximate orbit, which is just iterating forwards, jumping to the iterate backwards, and so on.
But you probably can do even it even faster, right? You can do 2 times in one step. Like you can compute F squared or F.
Oh, sure. Yeah. No, it's a totally trivial thing, but yeah, and you can use this if you want to design maneuvers, right? Because I mean, this gets a little bit more interesting, and Marian knows it very well, right? When you are near invariant manifolds and things like that, near normally hyperbolic manifolds, which I have not discussed yet, but you stay, and this is actually very useful. So this is what I call like when you are in periodic perturbations or things like that, this is extremely useful because this is the analog of what sailors used to do, right? So whenever you are, whenever the winds are favorable, then you are jumping right in the sea, you unfurl your winds, etc. And then when things are bad, then you stay near the harbor, right, which is the fixed point, and so on. And then when things are okay, then you make another excursion. And if you do this, then this is extremely useful. I mean, I didn't discuss it, but for periodic or quasi-periodic perturbations, and then you can get all sorts of interesting effects of instability. And it's actually quite practical. I mean, you know, you can do this in astronomical problems.
Any more?
No, it's a. I mean, I didn't discuss the practical algorithms, but it's extremely practical.
Any more questions or comments?
I had one question. Can you say a little bit more about the idea of Poincaré to solve quartic and quintic, I guess, polynomial equations?
Yes. The idea is that if you have this function, I mean, you see, the basic idea is that the sine and cosine satisfy this functional equation, right, with factor 2. And then this is related to the square roots, right? Yes. And if you can get a set of functions that satisfy very nice algebraic equation, and there is a very nice algebraic equation that you can factor it, etc. So if you can get things that have this f, which is a polynomial of a certain degree, then you can use this to sort of solve this equation, you can use your functions k to solve the equation. I mean, I can send you the paper because I have a copy of the paper. It's called the Transcendart Uniforms or something like that. It's a very obscure paper, and actually the thing that I believe that caused a lot of confusion is that Poincaré was quoting the wrong paper. But if you look at another paper that he wrote more or less the same year, etc., then you find it out, and then it actually works perfectly well. So, and then it makes sense because I mean, if you look at what he wrote in the book in Celestial Mechanics, then you see it says chapter 3 or chapter 4 of this paper, then you find this and you find the other. And then you look at the paper that he quotes and there is nothing. But if you look at chapter 3 of chapter 4 of the other paper, then it is perfectly there. So.
And maybe another historical question. So there was this prize that Poincaré had to win, I guess. Was it just a one-time thing, or was it ever given again?
I think it was only once, because I think it was because it was the 10th anniversary of the coronation of the King Oscar or something. I don't know. So.
Okay. Thanks.
But yeah, no, it's. I mean, this is kind of a small story, etc. But the interesting thing is that I mean, I'm pretty sure that this is the paper that Poincaré had in mind, because it makes a lot of sense. But you see, I mean, at the time, these equations, the only tool that they had was the method of majorants. And the method of majorants, when you have more than two variables, then two or more variables, then it becomes a bit mess. And turns out that these functions that satisfy the good functions, so people also discovered that the functions that satisfy these fancy doubling equations, etc., are elliptic functions. So if you use elliptic functions, you can solve the quintic. This is an obscure fact, etc. And I mean, explicit formulas, you know, yeah.
Nice. Anybody else? No? If not, let's thank Rafa again. And we hope to see everybody again next week on Wednesday at the same time as today, 3 p.m. 3 p.m. Eastern time.